Guys, oscillations. We get given these equations in the formula booklet. So normally you're just finding omega angular velocity so that you can use these in this equation here. Now this equation here is important because it describes simple harmonic motion. Simple harmonic motion is when A, acceleration, is proportional to x, which is displacement, but in the opposite direction. So if we wanted the maximum A max, the maximum acceleration, that appears when x is maximum. Now x is the displacement. When x is maximum, that is the amplitude. So you can have A max is equal to minus omega squared A, where A is the amplitude. So remember, if you want to know what maximum acceleration is, it's when you get maximum displacement. Now we get these two equations that we are using to solve for displacement. The reason why there's two, and they're exactly the same apart from this one's cosine and this one's sine, is it depends where you start measuring the oscillation from. Usually, if we were doing a displacement time graph, we'd start timing from when it's a maximum displacement, when it's its amplitude. Because if we were doing a pendulum, we'd pull it to its maximum amplitude before it started. Then it would go to 0, go down there, up there, to there. Now that, I believe, is a cosine graph. So we would use that equation to solve it for the displacement. If we'd started timing when the object passed the middle point, then we'd get a sine graph, and we'd use that sine equation. The last equation here, v is equal to plus or minus omega root of a squared minus x squared. Now, a squared is amplitude and x squared, that's displacement. Quite often, when we're looking to use this equation, it's to find the maximum velocity. Now, the maximum velocity occurs when x is 0. So when x is 0, this equation becomes plus or minus omega, the square root of amplitude squared, well, the square root of amplitude squared is just amplitude. So make sure that you can change these equations to find the maximum acceleration and to find the maximum velocity. Now, I've drawn already a displacement time graph, and obviously the biggest displacement you get is A down to 0 down to minus A. Okay, so that graph shows the displacement. Now remember, we have done this in class. We can turn this into a velocity time graph. And the velocity time graph, remember, if this is displacement time, the gradient shows us what the velocity would be. So here, I've got a maximum negative gradient. So that's going to be a maximum negative velocity. Here I've got 0 gradient. Here I've got 0 gradient. Here I've got a maximum positive gradient, and here I've got 0 gradient again. So my velocity time graph, which will correspond with my displacement time graph, would look like that. Now, if I wanted to label the axes, well, my maximum velocity, I've worked out down here, is omega A. So I can put omega A as my maximum velocity, and obviously down here that would be minus omega A as my minimum velocity. Okay, so this one here is my velocity time graph. Let's make this last one an acceleration time graph. Now, similar way, you can find the acceleration from a velocity time graph simply by looking at the gradient. So here's my maximum positive gradient. I can pop across in there. I've got a 0 gradient for that bit, a 0 gradient for that bit, maximum negative, maximum negative. So you can see my graph for acceleration is like that. Notice it's a mirror image of displacement one because acceleration is proportional to negative displacement. And I've worked out that my A max is omega squared A, so I can label this one minus omega squared A and this one omega squared A. So those are some of the graphs that you might need to know about for your simple harmonic motion. The other three graphs that you might need, we have plotted these ones before as well, are looking at how different things are related. So if we had an acceleration displacement graph, because acceleration is equal to negative displacement, is proportional to negative displacement, what that would look like is a graph like that. So we should be going through 0, 0 there. If we were doing a graph of acceleration and velocity, well, acceleration is a maximum when velocity is 0, and that's in either direction. Okay, acceleration is a maximum when velocity is 0. So a velocity acceleration graph, it looks like this. And similar way, a velocity displacement graph. Similar thing, you get the maximums when the other things are minimums. So we have a graph that looks like a circle again for that one. So the important ones are there, but it does say that we need to be able to graphically represent the other ones as well. Now, the other thing you need to know about simple harmonic oscillators is about the energy. So you can either picture a pendulum or maybe a mass on a spring. If we're looking at energy, and if this was the displacement, when it's at the end, it's got maximum potential energy. When it's in the middle, it's got minimum potential energy. That potential energy might not be 0. Then it's got maximum potential energy at the end. So that purple line is the potential energy. Now the kinetic energy would start at 0 and it would gain the exact amount of kinetic energy that it loses on potential energy, or whether that's gravitational potential or elastic potential. And then it would go back down to 0 again. So the important thing is on your graph that the total energy at any time, the total energy would be constant. So whatever the total energy is, this bit plus this bit must be, this bit plus this bit must add up to that bit. The total energy is constant. Now, that's for an ideal simple harmonic motion. However, we do have energy losses due to friction, air resistance. So what in real life the displacement time graph would look like is it would get less and less and less due to damping. Okay, I'm going to post this. There'll be another video soon about resonance. Carry on revising. Let me know if there's anything you want me to go through.